In the previous session, we have looked at graphs of linear and quadratic equations or functions. Now let's look at it for cubic functions. So we have f of x equal to x cube. X square and x are not there. Neither is the constant. In general, the cubic function is y is equal to f of x is equal to ax cube plus bx square plus cx plus b. Here a is equal to 1, b is equal to 0, c is equal to 0, and d is also equal to 0. So if we plot this graph, what do we get? We get this graph, and it has 4 parts. Looking at the equation, cubic part, that is ax cube, quadratic part, that is bx square, linear part, that is cx, and the constant d. Now notice that changing a changes the overall shape of the graph. Changing b moves the position of the turning points. Changing c changes the tilt of the graph. Changing d changes the y-intercept. Let's change a continuously. So do you notice the shape of the graph itself is changing? Let's change b now continuously. It changes the position of the turning points. Yes. And changing c changes the tilt or the inclination of the graph. So let's change c. Changing b changes the y-intercept. Changes the y-intercept means what? It will just go up or down. So let's change d. So look in the equation. It is changing continuously. Now, the graph of a cubic function intersects the x-axis at no more than 3 points. As of now, it is intersecting the x-axis at only 1 point. Later on, I'll show you when it intersects more than 1 point. Now, when a is equal to 0, f of x is quadratic. Of course, the other two should not be 0 then in that case. But anyhow, let's see. So when a is equal to 0, what happened? Everything has become 0. A is equal to 0, b equal to 0, c equal to 0, and d is also equal to 0. So our equation has become y is equal to 0, which is the graph of the line which lies on the x-axis. Okay, now let's make b equal to 1. So now what do we have? We have 0x cube, x square plus 0x. So it has become quadratic now. When a is equal to 0 and b is also equal to 0, it becomes the straight line what we had previously. That is the line which was lying on the x-axis. But if a equal to 0, b equal to 0, but c is equal to some value, then it becomes a line which is not on the x-axis. And if we change d, what will happen? That line itself will keep going up or down. Yes. So the point is, if the coefficient of x cube is 0, then it becomes a quadratic, provided of course the coefficient of x square is not 0. If it is also 0, it becomes linear. Okay, I think you got the idea. So let's go back to our original graph of the pure cubic. Now, when a is not equal to 0 and b equal to 0, c equal to 0, it is called pure cubic. When a is not equal to 0, b is not equal to 0, or c is not equal to 0, it is called adfacted cubic. Again, like before, discrete graph, the points are not connected. In case of continuous graph, the points are joined to form a continuous curve. So here I have drawn the continuous curve, but let us say I just plot the points. I just plot the points. Then it is a discrete graph. Now, of course, when we have discrete graph, when we plot only the points, it becomes difficult to visualize how the graph will look like. So the more points we plot, the smoother the graph becomes. So let's do one thing. Let's join these points. There's a point below and there are points above also. So let's join these points. So by just joining the points, we are not getting the actual curve or even a close approximation of that. Now here we have taken integer values for x. So let's take some decimal values as well. Yes. Now do you notice it is becoming closer and closer to the actual graph, which is this. So the more points we plot, the smoother the graph becomes. In non-linear curves, we need to find the turning points. Otherwise, it is difficult to plot the graph accurately. Looking at a discrete graph, we do not know exactly where the graph turns. So that is why the more points we plot, the smoother the graph becomes. But it is the turning points which becomes much more critical. Now, the values of A, B, C, D are treated as parameters. Once chosen, they remain fixed for a given graph, while x varies. The graph intersects the x-axis at, remember I said, the graph of a cubic function intersects the x-axis at no more than 3 points. So the graph intersects the x-axis at one point when both the turning points lie on the same side of the x-axis. So same side of the x-axis means what? Our y-intercept is above. So let's take the y-intercept above. So now it is intersecting the x-axis at only one point. It will intersect at 2 points when one turning point just touches the x-axis. It just touches it. So here there is 1 point here and 1 point here. At 3 points when the turning points lie on opposite sides of the x-axis. So something like this. So here 0.1, 0.2, 0.3. 3 points at which this curve is intersecting the x-axis. Now the slope of the curve varies throughout the domain, and hence the slope is equal to the slope of the tangent at any point. So let's take a point anywhere on the curve. This point can be anywhere. If we draw a tangent to the curve at that point, the slope of the curve is equal to the slope of this line. So in summary of linear, quadratic and cubic functions graphing, algebra not only helps us calculate, it also helps us understand relationships between quantities. In the examples above, each value of x gives exactly one value of y. When an algebraic expression assigns a unique output to every allowed input, it describes a special kind of relationship between quantities. Such relationships are called functions. So, we have seen linear functions, quadratic functions, and cubic functions, and some of their properties. That's it for now.